flipped classroom video for Maths AS Unit 1, Exhaustion and Disproof. First, we'll have a look at proof by exhaustion, and this is also known as proof by cases or the brute force method. So what we do is we exhaust all the possibilities by showing that they are true, and then the claim is true. So for example, we're asked to prove that n plus 1 cubed is greater than 3 to the power of n for all n less than 5 with n a member of the natural numbers. And there's some notation there. So, and some bonus notation. This is referred to in the first video for this proof section, so I won't go over it again. So the easiest way to deal with this is to draw up a table. So we have our n, then our n plus 1, then n plus 1 cubed, which is the left hand side of the inequality, and then 3 to the power of n. We pop the numbers in. Now we only need 1, 2, 3 and 4, and I'll refer back to that in a bit, but I've put 5 in just as a matter of interest because for some reason they've said for all n less than 5. Anyway, then we put the other numbers in. We can use our calculator or our brains depending, and so we can show that the 4 top rows do work, which proves the claim. The next one doesn't work, which is why they've stipulated n is less than 5, and that symbol is a greater than symbol with a line through, so it means not greater than, similar to not equal to. And we can then bracket those 4 lines and put our square there, which tells us that we've proven it. Now, I said I would come back to the numbers because, just as a little addition, we can set these sorts of things up very nicely on computers, and in fact there are famous proofs which have been done using computers. So that's just a little bit of an Excel spreadsheet. But notice I've got 1, 2, 3, 4. But if we go into the negative numbers, which actually we can't do for this because n is a natural number, but 0 is often considered to be a natural number, and this actually fails for 0. So in an exam situation they would make sure they were very clear on that, but it's interesting nonetheless to look at this. And in fact the size of n plus 1 cubed is greater than the size of 3 to the n, because of course if n is negative that makes it a negative index, so it's 1 over whatever the number is. But of course the sign is negative for the negative numbers for n plus 1 cubed, and so all the n plus 1 cubed are actually less than the 3 to the power of n. So stipulating what numbers you're using in these sort of things is essential, and that goes back to the idea of maths being watertight proofs. So if you're going to prove something, you have to state clearly what it is. And actually this question would have been better if instead of saying for all n less than 5, we said for all n between 0 and 5. The other thing is that if we stipulate between 0 and 5, we could even say that n was an integer rather than a natural number, because we've eliminated the negative numbers anyway. So, another proof by exhaustion: if x is a member of the integers such that x lies between 1 and 7, prove that the last digit of x to the power of 5 is indeed x. There's our notation. The new notation there is st for such that, and this is one for you to have a go at, so you might want to pause the video. We're now going to look at disproof by counterexample, and to disprove a theory we only need one example of where it is untrue. So there's an interesting link to science here. For a theory to be a scientific theory, it must be capable of being falsified, which means there must be some experiment we could do which potentially could show the theory to be false. Anyway, going back to maths, to disprove a theory we only need one example. So we have this theorem, b squared is greater than a squared implies that b is greater than a. Well, is this true? Oh, there's our notation, by the way. The arrow means implies, so b squared greater than a squared implies that b must be greater than a. Now for positive numbers that is going to be true. So what I'm going to do is choose a positive and a negative number. And if we choose a as 1 and b as minus 2, then when we square them we get rid of the negative. So we have a squared is 1 and b squared is 4. And then we have a situation where b squared is greater than a squared, but b is not greater than a. So that implication is not the case, and so the theorem is false. And we can see the thinking I was talking about here, and it comes from the fact that when we square numbers we have a not increasing function. It's a function that goes from very high up in the negatives down to 0 and back up again. And I've shown the example there of a couple of numbers where b squared was 3 and a squared was 2, but then we can see that a is in fact bigger than b because b was negative. We might notice here that we can make this theorem true by specifying the types of numbers, or the type of numbers rather, to which it applies. So if we were to stipulate that given a and b greater than 0, b squared being greater than a squared implies that b is greater than a, that is in fact true, and I'm not going to prove it here, but we can see on the graph that that's because if we restrict ourselves to only numbers greater than 0, then because it's an increasing function, then the theorem is true. And there's an interesting question here for you to ponder. Are visual demonstrations of these situations proofs in a mathematical sense? Well, I'll leave you to ponder that, as I said. So, another disproof by counterexample. Show by counterexample that the claim that for all p in big P, and big P is the prime numbers, so that means for all prime numbers 2 times the prime number plus 1 is also a prime number. And so we're going to try to show by counterexample that that claim is false. There's our notation for all, a member of, and then the new one, P, double line again like the other sets. So that's the set of prime numbers. And we could start off with a table, because if we're asked to do something like that, it's not going to be a massive prime number because nobody would be able to find it, certainly not in an exam situation. So it's going to be a relatively small p. So time for you to have a go at that, and you can see how many prime numbers you have to test before you show that that claim is false.